They dug until the ground answered back. A rusted hatch, once bolted to a low-slung Arctic building, sat welded shut beneath wind-thinned paint and a rim of permafrost, as if someone had tried to close off a question the world refused to answer. Around it, the tundra spread flat and patient. Inside the frozen compound there were cores and logs and the slow mechanical breath of machines that had once been convinced they could outpace geology. The story began in a world of flags and shadow maps. In 1970, in the middle of the Cold War, reaching downward became a way to show national muscle and scientific mastery. Governments funded ambition in kilometers, a hole that would pierce the crust, perhaps even scratch the edge of the mantle. Drilling was advertised as both a technical achievement and a statement, a contest of wills between nations who read victory into long vertical lines on a map. The Soviet program on the Kola Peninsula, what later became known simply as Kola, was born out of that mixture. Curiosity braided with competition, engineering focused through political lenses. If you like deep history and weird science, stick around for the rest of the story. There's a strange human aftertaste to every measurement. Kola's engineers designed a set of specialized tools for an unprecedented task. They used low-speed, high-resilience drills meant to grind slowly through rock that had never seen a bit. The project built a network of branched boreholes so that instruments could take measurements and retrieve cores without a single monolithic shaft. The deepest of those boreholes, SG-3, reached 12.2 kilometers. The working diameter was narrow, roughly 9 inches, so everything was a study in precision. How to twist, how to cool, how to lift a cylinder of 2-billion-year-old stone from beneath a continent. The program ran through decades, officially from 1970 until operations wound down in 1994, and left behind a meticulous archive of logs, samples, and instruments that had been coaxed into the dark. The project was not alone. Across the world, teams tried to answer the same question. In Germany, the KTB project in Bavaria pushed down to about 9 kilometers, and lessons from those efforts fed back into drilling practice. How to maintain near-vertical boreholes. How deviation and wobble could kill a mission as surely as a snapped drill string. American teams attempted their own deep drills in places like California and Costa Rica, but none achieved the same depths as Kola. The global pattern was clear. The farther people pushed, the more the planet pushed back. Depth was only the first measure. The cores returned more than raw stone. They returned surprises that forced scientists to rethink models that had seemed tidy on paper. Seismic surveys had suggested particular layering, sediments, basaltic flows, and then a transition to mantle materials at some predictable depth. What Kola found complicated that picture. Granite, a rock type normally associated with continental crust and expected at shallower levels, persisted far deeper than geologists had anticipated. Some reflections once interpreted as clear boundaries between layers turned out to be metamorphism, a reworking of rock under heat and pressure, rather than neat compositional transitions. Each sample was a riddle, the planet's narrative in compressed crystalline lines. Even more striking were the traces of the living past. In cores millions and billions of years old, researchers identified microfossils and organic compounds, chemical signatures that suggested life had left marks deep in the rock record. These were not living organisms pulled from the dark. They were preserved remains and molecules that bore witness to ancient biological processes. For biologists and geologists alike, the implication was profound. Environments once considered sterile or irrelevant could, under the right conditions, lock away traces of life. That discovery prompted comparisons, rhetorical but resonant, to what it might mean if someday missions on Mars turned up similar chemical footprints. It was not an equation of equality. It was an analogy meant to stress scale and significance, and then the answers changed tone. Engineers expected heat. Models had predicted temperatures rising with depth. Estimates put early expectations around 100 degrees at certain levels. What the instruments recorded was steeper. Temperatures climbed toward roughly 180 degrees Celsius in the deepest stretches. Heat was not merely a nuisance. It altered the material behavior of the rock and the reliability of equipment. At depth, rocks no longer behaved like rigid, brittle slabs, but began to flow and deform in ways more akin to plastic than stone. Porosity and permeability, the measures of how much void space rock contains and how fluids move through it, shifted under pressure. Voids closed, pathways altered, and fluids behaved unexpectedly. The very ground that had seemed to offer a straightforward record of time began to respond dynamically to being excavated. Those physical realities translated into grinding, practical problems. Drilling assemblies overheated, instruments failed, seals and electronics designed for cool, predictable conditions could not withstand the creeping convective heat and the pressure that flexed parts out of tolerance. Cores that had been taken under one set of assumptions now required reinterpretation in light of unexpected metamorphic processes. At the same time, political winds changed. Funding dwindled in the post-Cold War shift of priorities, and long-term support for such an audacious and expensive program evaporated. The project's end was not a single dramatic failure, but a confluence. Thermal limits that rendered further drilling impractical, mechanical and geomechanical behavior that defied existing solutions, and a financial-political environment no longer willing to underwrite the enterprise. Where precision instruments left off, human stories filled the silence. Workers who had spent seasons in the Arctic remembered the way the station rattled in winter storms, the taste of diesel in the air, and the oddness of taking home a chunk of rock that had never known sunlight. Locals, observing the abandoned compound and the welded hatch, began to tell other kinds of stories. Travelers would hear, as a piece of folklore, that the hole was a door to hell, or a throat to the planet's core. Those remarks lived in a different register, tourists' lore and cautionary tale, not evidence. Scientists treated them as part of the cultural aftermath, a reminder that the void left by abandoned science often gets filled with myth. Mini ganchos threaded the narrative. After describing depth, the thought surfaced that depth was only half the story. Before detailing the biological finds, the narration turned. And then, the rocks told a different story. At each shift, the attention moved from instruments to implications, from raw measurements to what those measurements meant for humanity's picture of Earth. Other programs learned from Kola's ledger. The German KTB team, for example, emphasized the importance of controlling vertical deviation and understanding the local geomechanical environment. Drilling is not simply about pushing down, it is about listening to how the ground responds and adjusting expectations accordingly. Engineering designs evolved to account for higher temperatures and for rock that behaved plastically rather than merely fracturing. The lessons extended beyond borehole technique to the philosophy of exploration. Assume complexity, expect surprises, and design for resilience rather than certainty. The image that endures is not only technical but emblematic. A metal hatch, welded to seal a doorway that engineers had once hoped to leave open. Around it, the building sat empty, windows opaque with frost. Cores catalogued and samples archived became proof that people had tried to read the Book of Earth by tearing out a page. The planet answered not with a voice but with laws, thermal gradients, material behavior, pressure regimes, and with a set of consequences that no amount of political will could override. The ground's response was physical, measurable, and unequivocal in its own terms. That answer carried a kind of moral quiet. Ambition had spurred extraordinary feats. Machines that could extract a continuous history from rock a dozen kilometers down, insights that reshaped seismic interpretation, and chemical traces that nudged the boundary of what scientists considered habitable or relevant. Yet the operation also exposed hubris, the assumption that a technological fix could simply be applied without accounting for natural limits. The end of Kola and the abandonment of its structures taught a more valuable lesson than any record of depth: the necessity of humility when confronting planetary complexity. They dug until the ground answered back, and what it answered with was not a judgment but a set of constraints. Heat, pressure, and time wrote back in data and failure modes, and in the end the project folded into history on the strength of cumulative realities. Thermal extremes that made further progress impractical, rocks that would not behave like textbook specimens, and the withdrawal of resources when the geopolitical moment passed. Folklore filled the silence left by science, and the welded hatch became a tourist photograph and a cautionary metaphor. The long shadow of that experiment remains useful. It reminds us that curiosity can carry us to extraordinary places, but it also reminds us that understanding often requires acceptance of limits. Scientific ambition and humility are not opposites but companions. Each question answered at depth revealed two more questions, each more nuanced than the last. The planet will respond to our probing, not with malice or mercy but with physics, gradients and flows and mineral rearrangements. Listening means preparing to learn from those responses. If this story has stirred your curiosity, explore further. There are full archives, documentaries, and playlists that trace the Kola borehole and its companions in Bavaria, California, and Costa Rica. Read the logs, see the cores, and watch how science adapts when the world refuses a simple answer. In the end, the rusted hatch remains a small, human object on a vast planet, a reminder that when we press in, the Earth will answer back in its own language.